So this chapter so far has been about the superposition of waves and then these concepts of constructive and destructive interference. So superposition, we know if there's multiple waves in the same medium at the same time, we simply find an overall or total displacement of the medium by adding the displacements of the individual waves at that specific location and at that same moment in time. If we remember, our wave is a function of both position, where in the medium we're talking about, as well as time. We've written this as a position of x and t, x assuming the wave is traveling horizontally in the x direction. That could certainly be y, so for a wave that's traveling vertically, or we could choose r, meaning a wave that is emitted radially outwards, equally in all directions. When we look at our wave, just a generic equation, I mentioned this in a previous video, everything inside the parentheses, the sign of all of that stuff, is considered the phase. Now, phi naught, this is the phase shift that accounts for initial conditions. The phase, phi, without a subscript, means just at this specific position, the specific time, it has a certain value. So just generically, if we have a couple of waves traveling from two different sources, they're coming to one common location, what we see in terms of the displacement of the medium ultimately depends on the difference of their individual phases. So even though the total displacement of the medium would be simply the addition of their individual wave equations, how those ultimately add up depends on this difference in phase between the two of them. Now, absolute value, just ultimately, how do they relate? As we mentioned before as well, perfect constructive interference. And to get this, remember, we have to have identical waves. So same wavelength, same type of wave, they'll have the same frequency, same speed. To get perfect constructive interference, the waves need to meet up in phase, which leaves us with delta phi of 0, or 2 pi, or 4 pi. We wrote this as a multiple of 2 pi, where m could be 0, 1, 2, 3, so forth. M here is not a mode. We don't use that term, or harmonic number. We don't use that term in this case. We just consider it a multiplier, but it is 0 or a whole number, suggesting that there's multiple situations in which two waves can constructively interfere. To get perfect destructive interference, this is where they met up perfectly out of phase. So one peak was added to the trough or valley of the second wave. And so when they added up to get the overall displacement was 0. We ended up with a delta phi. We wrote this generically as a multiple of 2 pi. But this m plus 1/2, using the same m values, because these two waves, as long as they are shifted a multiple of pi or 3 pi or 5 pi or 7 pi, they would meet up perfectly out of phase, and the peak of one would fill in the trough of the other. And we're talking about having the waves, they're identical, they have the same wavelength and frequency. So this bottom one, I think I can grab it and move it. If I move this where the peaks and the troughs line up, they're now going to add up to be 0 and give us that situation of perfect destructive interference. So this first shift was a shift of just pi radians. Whereas if I had my original, let's try that again. Had my original wave again, I could move it and get this peak to line up way down here, and that is still considered destructive interference in this location where both waves are still in the same medium. And so that would be a shift of 3 pi, going from where it was originally to now. So by moving that wave, we can still get the destructive interference. And similarly, we could move the wave where a peak would line up with another peak so that it would be in phase as well. Oftentimes, we use these equations and we rewrite them in terms of wavelength and a distance, a shift in distance. So let's see if I can grab this again. We'll just grab this part. I know right now these peaks are lined up. So right now these waves are constructively interfering. The amplitude would be twice as large. If it was sound, it would be louder. If it was light, it would be brighter. In terms of wavelength, I know I can move this bottom wave, and as long as the peaks still line up with the other peaks, then we're still going to have constructive interference. Now, in terms of a phase shift, in terms of an angle, I just moved that bottom wave by 2 pi radians, by one whole cycle. I moved this peak from where it originally was to the next place there was a peak. That would be, if I actually could measure a physical distance, that would be a wavelength. It turns out we can write these shifts in terms of wavelengths as opposed to angles. Right now, these are in terms of radians, a shift in radians. Both of these are written in that way. But we can do that in terms of wavelength as well. So delta phi, in general, that's for constructive or destructive. This means I'm taking kx minus omega t plus phi naught for one wave. So I'm going to put a subscript of 1 on the x and the phi. Now, I did not put it on k or omega or t, and that's because to get these situations of perfect constructive or destructive interference, the waves have to be identical. And since k is the wave number, 2 pi over wavelength, they have the same wavelength. If they don't, we cannot get these perfect situations. Omega, similarly, 2 pi f, they will be the same because we're working with identical waves. And t, time, we can only observe something at one moment in time. So we can't talk about these two different waves interfering at different times. That just doesn't make sense. So our difference in phase is we're subtracting the difference between these two phases of the two waves. Since k is the same, omega and t are the same, so those will subtract out. We end up being able to say that this phase difference between the two waves is equal to k delta x plus delta phi naught. The delta phi naught represents the initial conditions. If the waves are in phase as they leave their source, then delta phi naught is 0. They're not shifted relative to each other initially. Delta x ends up representing the difference in distance. Difference in distance one wave travels compared to the other. So, for example, let's say we have two speakers. So they're both connected up to the same stereo system. They emit identical waves in phase with each other. And we wanted to look at constructive versus destructive interference. So if I have speaker 1 and speaker 2, and by the way, if they're emitting identical waves, right now we're assuming just one frequency and wavelength, which would be really annoying to listen to, that same frequency the whole time. That's a total side note. So both of these are emitting waves. They're longitudinal, of course, because they're sound, but drawing a longitudinal wave is a challenge. They're emitting waves in all directions. And so some of these waves are crossing and interacting at the same location at the same time. So when we're talking about delta phi is k delta x plus delta phi naught, since we're going to right now assume the waves are in phase as they are emitted, this is going to be 0 because the waves are in phase as they are emitted. Meaning, as they come out of the speaker, they're in phase with each other. Ultimately, when we look at any one location that both waves travel to, we're trying to find out if they're meeting up in phase or out of phase or somewhere in between. And that's what the rest of this equation is going to represent. We know for constructive interference, delta phi has to be a multiple of 2 pi. If I set that equal to k delta x, I'm going to replace in here, k is the wave number, which is 2 pi over wavelength. This tells me that delta x is a multiple of a wavelength. If one wave travels a whole wavelength farther than the other, or 2 whole wavelengths farther than the other, or 5 whole wavelengths farther than the other, as long as it's a whole number, then we are going to have constructive interference, meaning twice the amplitude. If it's sound, it's going to be louder. If it's light, it's going to be brighter. M equals 0 refers to delta x of 0. What that means is that the waves from speaker 1 versus speaker 2 traveled the same distance to get to that location. Delta x is simply that difference in distance, absolute value. If both waves travel the same distance, then delta x is 0. That is going to be a point of constructive interference. If we were standing at this point and we were listening to these speakers, the sound would be louder than if we were listening to only one of the speakers. That's what that means. If m is 1, we get delta x is equal to lambda, meaning one of these waves traveled exactly one wavelength farther than the other one to get to us. But because of that one wavelength shift, those two waves are still in phase. And so we still hear this louder sound. M equals 2 means delta x is 2 wavelengths. All that means is one of these traveled 2 wavelengths farther than the other one. And so we still observe the constructive interference. So with sound, we would hear that sound louder with those two constructively interfering compared to just one speaker alone. Destructive interference is when these guys meet out of phase, where we have that m plus 1/2 is 2 pi. Either way, delta phi is going to equal k delta x. We're assuming these waves are emitted in phase with each other. So if we plug in k as 2 pi over wavelength, we find that this difference in distance has to be a multiple of half a wavelength. M, the way we write this with this quantity of m plus 1/2 is so that we can use the same possible m values for both destructive and constructive. M equals 0 means a difference in distance of exactly 1/2 of a wavelength. The waves were in phase, but one traveled 1/2 of a wavelength farther, which means that as those waves reach that same location, they are perfectly out of phase with each other. M equals 1, delta x would be 1.5 wavelengths farther, and so forth. Destructive would be quieter. The sound would be quieter. If we could ensure we were listening to only these two sounds, technically the sounds would cancel each other out. But realistically, if we're in a room, we're listening to these sounds, there's going to be waves reflecting off of walls and tables and floors and ceilings. And so we are technically listening to more than one wave. So ultimately, what we need to do is in any given, didn't mean to slide the video section around. Let me pull that back down. Ultimately, what we have to do is, knowing where the sources are. So again, like these two speakers, and knowing a location that we're talking about, an observer being, we have to analyze how far the sound, in this case, travels from speaker 1. Similarly, we have to find out how far the sound travels from speaker 2 and find that difference. If that difference happens to be a whole multiple of a wavelength or 0, then we know we have a situation of constructive interference. Or if this difference that we calculate is some multiple of half a wavelength, then we know we have a situation of destructive interference. If it's something in between, then we have something in between. We don't have either perfect constructive or destructive interference. Excuse me. So we're going to go through a few examples here and show you how to apply these equations.